Hello everyone, I'm Karnalim, and on this occasion, I will explain my research entitled Automated Reporting of Code Quality Issues in Student Submissions. I'm with Simon, William Chivers, and Billy Susanto Panca. First of all is the background. So the code written by computing undergraduates is expected not only to function well, but also to be of high quality. Therefore, a number of automated tools to check the quality of one's code have been developed. However, general purpose tools often cover code quality issues that are not relevant for academia and give explanations that are somewhat too technical for novices. Consequently, a number of dedicated tools for academia have been developed. But still, using such tools can be challenging because they either require the use of a particular integrated development environment, they are not readily integrated in both IDE and assessment submission system, and they need both historical data and manual labeling. So, as the contribution, this paper proposed an automated tool called CQIS. It stands for Code Quality Issues Reporter, which can be integrated in many teaching environments. Why? Because the tool is embedded in assessment submission system and reports code quality issues for each student submission via static analysis. Instructors can thus freely choose their IDE for the students, and they are not required to provide historical data and do manual labeling. In this research, we have two research questions. The first one is, do students with CQIS have fewer code quality issues in their submissions? And the second one is, are students with CQIS explicitly aware of various aspects of code quality? So now we will discuss the tool first, CQIS. So it currently works for Java and Python submissions. It identifies 32 Java code quality issues, 8 concerning comments and identifier names, while the remainder are adapted from check style, considering their academic relevance and rewarding the explanation. For Python, CQIS identifies 20 code quality issues, 8 concerning comments and identifier names, and the remainder are from flag 8, taken in the same manner as check style for Java. CQIS, the code, and the documentation are publicly available. You can see the link in the paper. CQIS can be embedded in other systems since it is designed as a library with console-based arguments. So it accepts a student program and then generates an HTML page that reports code quality issues. So this is the example of the HTML page. So first, it has general guideline for high quality code, and then it also releases code quality suggestions and provide detailed explanation. And lastly, it also maps the issues in the student's code. So these are Java code quality issues that are covered. So there are like 32, and yeah, you can read the detail in the paper. And these are Python code quality issues. There are 20 of them. So now we will move to evaluation, which is addressing the research questions. First, we will address the first research question, which is fewer code quality issues. So how this can be measured? So this is measured by way of 4 quasi-experiments, each of which compares student code quality issues from 2 academic semesters of a particular course. All of the experiments can be seen in the table. So we have 4 courses: business application programming, advanced object-oriented programming, data structure, and introductory programming. So for each quasi-experiment, first, we collect student submissions and then group them based on their corresponding assessment tasks. In offerings that have 2 classes, 1 assessment offered to both classes is considered as 2 separate assessments. For each assessment task, it is language-specific code quality issues are identified and counted with a modified version of CQIS. G01 to G08 and P01 to P08 are not reported since their effectiveness has been discussed in our previous study. You can see the study in the paper. Average number of code quality issues from two offerings are compared for each issue and for all issues combined. The significance is then validated with two-tailed unpaired t-test with 95% confidence level. So this is basically the result. Reported code quality issues with significant and substantial differences. As we can see here, many of those are a result of the first experiment, followed by the second, third, and last. We will discuss one by one. So first experiment. So students with CQIS have fewer code quality issues in their programs in general because the assessments are about developing GUI applications. Given that the solutions are usually long and complex, student submissions naturally have many code quality issues that can be reminded by CQIS. Further, students are more encouraged to read and to see the report, given that code quality is part of the marking. Students with CQIS appear to be specifically aware of the expected Java declaration order, where static variables should be declared first, followed by attributes, constructors, and then other methods. They also learn not to put too much code in one line. Students might see both issues reported a lot, given that they arise quite frequently. 5 other issues arise less frequently among students using CQIS. First, brackets after variable name in array declaration, lowercase constant name, empty cache block, missing or unnecessary line separator, and too many statements in one method. All of them are relatively easy to fix. G19 falls into this category, still considered easy to fix because most of the long methods are GUI-related methods, and the statements do not rely on in-method results, so it is easy to break them down to smaller methods. G09, G23, 25, and 27 do not arise in either the control and intervention groups. Students are already aware that the use of abstract prefix should be consistent with the use of abstract classes, and non-static attributes should be assessed with the keyword this. Overly deep, nested looping, and try-catch are also not expected in these assessment tasks. Moving to the second experiment. So students with CQIS have comparable code quality issues with those not using it. Although students using CQIS might have greater awareness of code quality, the impact might be diminished by the fact that assessment of the control group have longer completion period, like 3 or 4 weeks per assessment, and students in this group have more time to reread and check the quality of their own code prior submissions. Students with CQIS have fewer code quality issues related to unnecessary parentheses. They appear to understand that expressions with unnecessary parentheses are prone to misinterpretation. G20, which is overly long line, and G22, missing braces in branching or looping statements, are the other two issues with substantial differences. But these differences are in favor of the control group. Why? With more limited time in completing assessments, students with CQIS appear not to prioritize fixing these issues. Long lines and missing braces do not substantially affect code readability. Overly deep nested looping is the only issue that occurs in neither control nor intervention group. The assessments do not expect such complex loops, as they are mostly about developing business applications. Moving to the third experiment. So students with CQIs generally have fewer code quality issues, which is interesting given that code quality is not specifically considered in the marking of the intervention group. Students with CQIs appear to understand that getting used to writing high quality code might be useful in the future. P10, which is missing space after comment opening, is the only issue with substantial reduction. This is expected as the issue is common and easy to fix. In both control and intervention groups from the third experiment, 3 code quality issues never occur. First is compilation error, as Python mainly relies on an interpreter. Second, improper use of break and continue, as these keywords are not specifically taught. And duplicate function parameter, as function parameters seldom have similar names. Now, moving to the fourth experiment. Students using CKIs have comparable code quality issues overall. The assessment expects short solutions, and code quality is not considered in the marking, so it is really expected. P10, which is no space after comment prefix, is the only issue with substantial reduction on students with CKIs. The issue can be fixed easily even without programming knowledge. There are 9 code quality issues that do not arise in either the control or the intervention group. 6 of them are related to Java, like inconsistency in abstract class naming, inline conditionals, lowercase constant attribute name, overly deep nested looping, overly deep nested triads, and access to non-static attributes without this. The concepts underlying these issues are not covered in course materials, and the assessment task is somewhat too simple. The other 3 code quality issues that do not arise are related to Python, which is compilation error, as this kind rarely happens, improper use of return, as function and methods are seldom used in this assessment task, and duplicate function parameter, as each function parameter is expected to have unique name. Now we'll move to the second research question, which is explicit awareness of some aspects in code quality. So this is addressed by asking students to list up to 3 remarkable pieces of information that they learned while using CKIs. The survey was performed at the end of semester in all intervention groups. 107 students responded to the survey and together mentioned 18 distinct remarkable pieces of information. So among the provided information, general knowledge about high quality code is noted by most students, 47. This is expected given that CKIs aim to improve the quality of submitted program. The second most remarkable piece of information is that programmers should use declarative identifier names, variable names in particular. So mistyped names sometimes occur, and while CKIs do not always provide good spelling correction, it can at least report the issue. The next 2 remarkable pieces of information are not to write too much code in one line and to use white space for readability. So while completing assessments, many students focus on how to complete the assessments. They can easily overlook putting appropriate white space, including line breaks, to enhance readability, and CKIs can help for that. Where to put comments, more declarative comments, and more efficient syntax are 3 other remarkable pieces of information that were listed. These are mostly noted by students of business application programming and advanced object-oriented programming. Because in these courses, the use of comments is explicitly encouraged and is considered as part of the marking. Further, due to the advanced level of their course material, it is more likely that some students will begin by writing poor quality code and will then revise it to improve the quality. The remaining remarkable pieces of information are noted by only a few students, like adequate use of braces and/or parentheses, removing unused code, expected order of declaration in Java, adequate use of semicolons, clarity in inline conditional, clarity in complex Boolean expressions, consistent identifier naming style, difficulty of expanding code with low quality, need for space after comment prefix, need for braces in branching or looping statements, and writing one statement per line. We have grouped and analyzed the responses for each courses, but since the findings are fairly comparable to the general findings described above, we choose not to report these results. So, as the conclusion, this paper presents CKIS, an automated tool to report a selection of code quality issues. Students using CKIS are likely to have fewer code quality issues in their submissions if 1. The assessments expect long and complex solutions. Second, code quality is considered as part of the marking. Students using CKIS also become more aware of aspects of code quality, mostly pertaining to readability. Our study has limitations, and that entails future work. First, the evaluation was performed only at one institution with a moderate number of students. Replicating the study at other institutions with more students might strengthen the findings. Second, student awareness of code quality was addressed only by asking students to list up to 3 remarkable pieces of relevant information. Some lessons that they have learned might not be reported as they are not in the top 3. Future work might list all knowledge aspects of code quality and ask students which aspects they believe have improved. Thank you. In case you have any questions, you can contact me by email.